Hello, everyone, and welcome to today's session as part of the Startup Energy Transition Week Online. My name is Emma Krause, and I have the pleasure of speaking with Christoph Beuttler today from Climeworks. I'll give a short introduction to each of us, and then I will let Christoph take it away with his presentation. I work for Adelphi GmbH. I'm a project manager there on the carbon markets team. Christoph is the CO2 Removals Manager at Climeworks, and for those who aren't familiar with Climeworks, it's a technology that's been created, a frontrunner actually, for the world's first commercial carbon capture technology. And Christoph is going to walk us through how this works, and we're going to get into at the end a bit of a discussion about the implications around this technology and particularly the scalability, which will be something I'll be curious about. So Christoph, with that, I'll leave it to you.
Thank you, Emma, and thank you, Dana, for putting on this important event. I'm going to share my screen, and I sincerely hope it does work. So I hope you can see my presentation in full screen and me as well now. So yeah, thank you for listening. What I want to talk about is carbon removal technologies. I know that the talk is titled Carbon Capture Technologies, but there's a slight difference which I'm going to go into. But I want to start with revisiting the problem. So why are we trying to remove CO2 from the atmosphere? So as most of you know now, we need to achieve net zero emissions at some point as soon as possible. Globally, we will most likely achieve this or we hope to achieve this in 2050. But that also means we need to remove CO2 from the atmosphere for two reasons. First of all is we will have unavoidable emissions, unabatable emissions, and we need to neutralize them. And the second reason is that we need net negative emissions at gigaton scale, because net zero 2050 already means we will likely emit too much carbon into the atmosphere. So we really need to think about ways to get the CO2 out of the air again. And this is why at Climeworks we have developed a technology that is known as direct air capture. And I quickly want to walk you through that before I want to share two examples in more detail on what we can do with direct air capture. So this is our solution. This is actually our generation, the older generation that is already commercial at this moment. So we're delivering CO2, for example, to Coca-Cola HBC for their mineral water Valsa or to greenhouses. And it's a modular approach. So the 40-foot container is our unit of operation. We can use only renewable energy as an energy source, and we already have low emissions at 10 to 5% over the whole life cycle. And this is important because if you're in the business of emitting CO2 from the atmosphere, you better make sure that you don't emit more than you remove. And yeah, we are the world's first company doing this. So how does this work? I'm not a technical person. My background is in management and economics, but I'll try at a very simple approach. So we have made a filter that is highly selective and only CO2 sticks to it. So we move a lot of ambient air through our machines and the filter becomes saturated with CO2. When this is the case, we close basically the doors and we heat the unit to 100 degrees Celsius, round about there, and the CO2 is released, concentrated at about 98.5%. And with this CO2, you can then do basically two things. So the first one is you can basically replace fossil feedstocks for fuels and chemicals. And the way this works is by closing the carbon cycle. So one approach would be you take CO2 from the atmosphere, you combine it with, for example, green hydrogen, you make methane, green methane, and you can then Fischer-Tropsch and you arrive at a drop-in fuel to decarbonize, very hard to decarbonize or defossilize rather, industries like aviation. And when the fuel is burned, the CO2 is emitted into the air and the cycle starts again. Obviously, there are some residual emissions to this, but we foresee this process can be 85–90% net CO2 effective. And also, E-fuels burn a lot cleaner, so emissions from soot or other chemicals are a lot less or non-existent. So that makes the climate effect of aviation in this case a lot smaller. And what is true for this, you can do with any hydrocarbon chain. You can basically, with renewable energy and CO2 from the atmosphere, you can start building your hydrocarbon chains and make your products from these. And why is it important to take the CO2 from the air with machines? Well, there are two things that I want to highlight. The first one is that if you take CO2, for example, from a fossil point source and reuse it to make an e-fuel, which is already great, you still have a delayed emission because you reuse the CO2 once, but when you burn the fuel, it ends up in the air. So with this, you can really make, achieve close to carbon neutrality with your fuels and materials. And the second reason is there's obviously another way to take CO2 from the air, and that way is plants. But if you want to do this at a very large scale, we don't have enough space to achieve this. So if you were to satisfy the EU transportation energy demand with first generation biofuel, you would need this large gray circle that you see on the slide to satisfy the European demand, and that's larger than the landmass of Europe. So you need something that is basically has a smaller footprint. And our system that we have developed, you can achieve that with about 15,000 square kilometers. So it's a lot smaller. Now, the other thing that I tried to highlight at the beginning was that we need to have negative emissions. We need to do carbon removal. We need to clean our atmosphere to achieve the climate goals. And again, this is possible with direct air capture. You can take CO2 from the atmosphere, and we have, with our partners at Carbfix, developed a way to store this underground. And what we do is we don't sequester it, so we don't store it in a liquid form, but we mineralize it. So it turns out that in certain locations on the planet, you have very favorable conditions that, where the right pressure and minerals and etc. in the ground make the CO2 mineralize within 2 years. So it's already, it's a very safe storage, and that is already commercial and works. And with this, I'm very pleased to announce that we have a new generation, which you can see on the left. We're now building another plant in Iceland. In total, we have 16, but we're now building another one that is bigger than all the other plants we have combined, and it's also operating on a new technology that looks slightly different, but it's also more efficient. It uses, for example, 40% less steel over the whole lifetime per ton. And we are really happy that together with our partners in Iceland, we can make this happen. And it's something we developed in the past 2 years, and we have started building, and we will be operational with this plant in the beginning of next year. Obviously, Corona has put a slight damper on it, but we're still confident that end of Q1, we're sequestering the first ton of CO2. And this brings me kind of into the bigger picture. So I said before, we need to become really big to we call it climate relevant. So I guess we spent the last 3 years to create a niche market for CO2 from atmosphere. As I said, we deliver to Coca-Cola for their mineral water, Valsa. We deliver to greenhouses and other niche applications, but really now the time is to start scaling up. And this is kind of now at a stage where we also will try and enter mass production and build bigger and bigger plants. So over the next couple of years, we're already working on volume production, plants with 50,000 tons per year. And this is an example of how they might look like. And from 2025, we really, want to get into the global rollout. This is very ambitious, and we do realize that for a smallish scale up with now 120 people, this is an ambitious target. But as I said, and we'll go into again in the next slide, this is really necessary, because We have 30 years to arrive at gigaton scales, and if you look at the scale-up rates this requires, we need to work fast. Before that, again, this is already commercial, so we're offering our CO2 removal services to individuals. So you can go to our website and subscribe in certain tranches per month, but you can also just call us if you are a larger business, and we can develop a B2B agreement so you can achieve your climate targets or provide removal subscription to your employees. And again, with the negative emissions or the carbon removal, the same picture emerges. Obviously, you can do afforestation, you can do things like bioenergy with carbon capture and storage, or other new technologies that are not yet commercial, like enhanced weathering. But again, with direct air capture, this becomes really, really, really space efficient. And like before with the Efuels, that calculation you see on the right hand side at the bottom includes the renewable energy that we need to run this whole system. And to give you a feel for the footprint, about 96-98% of the footprint are just PV panels, and the rest is the direct air capture units. So this is a calculation on how to remove 8 billion tons per year from the air, and we need a surface area of about 20% of Iceland to do this. So you can think of it as an AC conditioning system for the planet. Again, what's really, really important here is to distinguish between carbon capture and carbon removal. So carbon capture from a fossil point source, what you're doing is you are hindering a CO2 molecule from entering the air. So you're hindering an emission to happen. And with direct, you make a negative emission or carbon removal possible. And I think the challenge that we are facing globally, apart from obviously mitigation and reducing emissions, which should always come first, and also because of the costs, economically makes sense to do first. And the challenge will be in the next years to design also appropriate policy mechanisms that allow the scaling of these technological-based removal approaches before we hit the limits of the bio-based approaches, like, for example, afforestation and bioenergy with carbon capture and storage. Because if we want to achieve the Paris goals or our climate goals, there will be a point, the science is very clear on that, where we will run out of sustainable biomass in order to remove CO2 from the atmosphere. So with this, I thank you very much for your attention, and I'm happy to take questions. Thank you.
Thanks very much, Christoph, for the really interesting and informative presentation. I have a couple of questions I'd like to put your way. The first of which, sort of just a stage-setting question for you, so we can get everybody a sense of a picture. When you say unabateable emissions, what kinds of emissions are we talking about here that can't already be addressed by something like an emissions trading system or other regulations that are in place that can encourage them to abate?
Yeah, that's a good question. So I think that there are two things in that. So first of all, there are things that are technically hard to abate. For example, aviation. Because of the energy density of batteries, it is very unlikely that we will have long-haul commercial planes in the next decades. So you really need to find a way to defossilize or close the carbon cycle with molecules rather than electrons. So this is the mechanism I described that becomes important there. And then there are other industries like, for example, cement, that are hard to abate, but there you can do carbon capture. So you can remove the emission directly from the cement plant and sequester it back, underground. Okay.
Yeah, that makes sense. And especially those big heavy industry, those big heavy industries, they're one of the ones that I think are sort of the stickiest to figure out how we're going to get them to reduce emissions to the level that we need. Okay. Well, then the next question I'd have is, this was a hardware and tech startup, and the first of its kind, from my understanding. So what are some of the obstacles that you had to overcome in order to be able to be talking about the kind of scale you are by 2025?
Yeah, well, we're not the only one. So there are 3 big ones and a few smaller ones now, and we are the first that is already commercial. And the obstacles, well, there were many. So a few years ago, the opinion was this can't be done, and then we went out and demonstrate that it's possible. And I think now we have to demonstrate that it can be done cheaply, and that all these value chains also need to be demonstrated. So obviously the shortest value chain is taking CO2 from the air and then mineralizing it underground. But recently we demonstrated that the fuel cycle is possible, and obviously we try to commercialize that with our partners. And I think cost is a question hanging over all of these. But as I said, in scenarios like aviation, there are really no alternatives for this.
And what does that cost look like to get it to a cheap point? Because I've done a bit of reading on different removal and capture technologies, and absolutely agree that they're needed in order for us to meet the sort of net zero emissions targets that are essential. But what does reducing that cost look like? Is it a piece of scale? Is it having to capture a substantial part of the market? What's sort of the strategy for proving that, as you said?
Yeah, so I think what we are trying to do, at least, and I think there are 2 main differences within direct air capture. So one is solid sorbent and one is liquid sorbent. And we have the solid sorbent approach. So we can use renewable energy, and we can build smaller modular plants. So we're trying to go in the niche markets, like for example, for the drinks, for Coca-Cola, and then from there move into less niche markets where it's more commodity and the price comes down, but the volume comes up. And I think there are 3 main topics. So one is capex, so we need to move into automated mass production. The price will come down significantly. Second one is process and sorbent. Over time that becomes more efficient. New sorbents are tested, so that brings the price down. And the third one is obviously this is energy intensive, so renewable energy and the cost of renewable energy is also a factor that drives down the price.
Yeah, okay, makes sense. I'm going to pivot to a question from the audience now. They'd like to know what kind of absorbing technology your system is using and whether it's based on MOF.
Okay, I can answer the first part. I cannot answer the second part because I don't know what MOF means, and as I said, I'm not a technical person. So yeah, the little things I know and can tell you is we're using a solid sorbent, and I've already, I think, in part answered that. It can desorb at 100 degrees Celsius. And the other way to do this is things that Carbon Engineering does, a company in Canada. They use a liquid sorbent, but there you have to desorb at 700 to 900 degrees Celsius. So you need to have a heat source, which is likely to be natural gas, and then you have to co-capture the CO2, the fossil CO2 part, which then over a full cradle-to-grave LCA, you have a different efficiency. And yeah, that's, I think, as far as I can go into it. I'm sure you understand that we are a private company, and sorbent is one of our very, very safeguarded things. And yeah, I'm not able to go into the very details of the technology there.
Okay. Thank you for trying to do it to the best of your ability there. A question that comes up to me sort of from the environmental side is the real crux of this being an effective technology is that there's certainty that the CO2 is going to remain captured and not be released into the atmosphere. How can you really ensure this certainty? What sort of processes are there to make sure it doesn't go back in?
Yeah, so I think this is a big topic, and obviously if you look at afforestation as a removal tool, we all know about the forest fires, and then, you know, then your removal is obviously gone, and when the trees decompose, it's the same thing. So what the technical solutions do is what we do is we put the CO2 back where it came from, right? So you can either use depleted oil wells, or what we do is we use a certain porous rock where we inject the CO2 in, and then through the right amount of pressure, heat, and other minerals, the CO2 reacts there and becomes basically limestone in a depth of about 2.5 kilometers. And this is possible in various places on the globe. We do this in Iceland, but there are other places. In general, it's places where you have volcanic activity. And because the CO2 is stored underground and it becomes solid, it's basically gone forever, for tens of thousands of years. And even, you know, should there be an earthquake or a volcanic eruption, this is stored. So this is really important to us. And this is, you know, we're really proud that we could, you know, with our partners at Carbfix, demonstrate this.
Yeah, absolutely. Okay. I'm going to pivot now to another question from the audience. Someone's curious how you're going to interact with companies using carbon dioxide instead of steam in power plants. Are you aware of this happening at the moment? And would this potentially be an opportunity for somebody like a Climeworks?
I'm not sure I'm aware, or I understand the question fully. Let me think about it for a second. So using carbon dioxide instead of steam for what would be my question back, I guess?
To power the turbines that would in turn produce in the power plant.
No, this is completely new to me. So that sounds very interesting. I'm not aware of that yet. Okay. I guess our technical team will be, but I'm not from the technical team.
Fair enough. Then I'll posit a policy question to you then, because you did speak to the fact that the policy context is going to be very important for removal strategies. And particularly you spoke about green hydrogen, and we're seeing countries around the world trying to think about how to put those policies in place. What sorts of content, like what key policies are you seeing being considered or either in place that are particularly helpful for removal strategies? And are there some that are actually rather challenging for you to work with? Yeah.
So I think in general, the challenge here is for us to have policies that catch us at the current price point of where we are currently, and take us with them so we can scale. And currently we are at 600 per ton, and there are, you know, yet there are no general policies where we can hook onto. But there, you know, at the moment, what's really exploding is globally is the funding for direct air capture. So the EU Innovation Fund, you know, the UK government has had a 100 million package, the DOE in the US. So that's very interesting. And I think in general, what seems to be happening is that in Europe and well, now also, you know, China and other countries, there's this way to start with a net zero goal, and then, you know, then that kind of, I think, for the first time then forces everybody to think about, so how can we get to zero? Then usually there's the realization that there are unavoidable emissions, and then you can start calculating how much biomass do I have. Obviously, we always would want to highlight that you shouldn't rely on importing biomass, because if everybody does that globally, there's a problem. And then, you know, roughly, you know, how much direct air capture or technical solutions you need for your scenarios, and then you can design policies accordingly. So in our view, carbon contracts for difference would be an excellent tool to trigger the technologies and drag them down the cost curve. But, you know, the US has approached this from a different angle. They don't have a net zero goal, but they have the 45Q, which is a law where you are paid for putting carbon into the ground. And they also have the low carbon fuel standard, which is a law where you can have a certificate on your emissions reductions. And if you combine these two, the 45Q is at 50 per ton, low carbon fuel standard is at 250. That's already 250 per ton, sorry, in total, is already a very attractive tool to trigger investment into these industries. But there will be, I think the thinking needs to evolve around how can I design proper policy tools that bring the cost curve of these different technologies that we all need in addition to the natural solutions, that brings them down and takes into account that they all react differently.
Mm-hmm. Yeah, so an easy task for the policymakers, I think, yeah?
Very easy, exactly.
Okay, we're coming up on half past, so I'm gonna pose one more question to you. I wanted to speak about sort of the environmental consequences of what you're doing, because as you mentioned, you've got these facilities in Iceland that are storing the CO2 and the capture, and I'm curious about sort of the environmental consequences of this, negative environmental consequences, and if this is sort of taken into account when calculating the sort of the CO2 footprint, and whether there's any sort of calculation actually of CO2 release during production as well.
Yeah, so as I hope to have gotten across, you know, we think big at Climeworks, and we want to become climate relevant and reach gigaton scale. So we think about, are there enough raw materials to go down a certain path? Are there any negative environmental impacts? And we always advocate for full cradle to grave LCA. So really look at the whole picture. And there's one coming out soon that looks at this in very detail. What I would like to stress here, in addition, is that, you know, climate science already knows that we cannot make the Paris goals without these technologies. Otherwise, the world would have to become net zero pretty much very, very soon. So current calculations say 2028, depending on when the carbon budgets are used up, which we won't make. So then it becomes a question of where's the least risk. And so because we have left it too late and we have emitted too much, we now need to outweigh the risks and benefits. I think with direct air capture, the environmental impact is very low if we design it correctly. If we rely too heavily on biomass, we will put more pressure on food prices. So it is the whole, to design the whole system well is a big challenge. But I think if done right, the risks are very low, and there are also co-benefits. This will create new jobs. This could bring renewable energy to new places on the globe, and so forth. So there's risk and also opportunity.
Okay. Yeah. Okay. It's a fair point to see what, based on where we are, if this is really the solution, then is this the way to get there? Then I'll ask one more here, sort of in that same vein. The removal process, it's quite energy intensive. How do you guarantee that there's a sustainable operation to the Climeworks solution? What does that look like?
Yeah, I'm aware of this argument, and I think there are two ways to look at this. So one is obviously economically to say, okay, we're using more renewable energy for this. Can this be used in a better way? And the other way is to say this would also drive the demand for renewable energy, and therefore, you know, also contribute to making it cheaper and scaling it even more. I think, you know, I'm not a global expert on renewable energy, but from what I'm told, you know, renewable energy can scale, and it can scale to 100% renewable energy systems. And experts also believe it can scale to include things like direct air capture. But we need to get a move on, basically. And I think this is the world we see at Climeworks. Is obviously, without a world run on renewables, it wouldn't make sense to deploy direct air capture at scale, because if you use a coal power plant to run our machines, they wouldn't be, you know, net CO2 efficient. So yeah, probably that's my answer. Okay.
Yeah. Okay. So basically, you're seeing the opportunity, and Climeworks is moving in that direction, betting that that's where we're going. Well, we're just at half past, So I think I'll wrap us up here with the message from Christoph of we need to get a move on and continue the momentum around diminishing emissions and meeting those net zero targets. Thank you to everybody who participated today and watched us. We appreciate you attending, and thanks again to Dana for the opportunity. It's been a pleasure, and enjoy the rest of the Startup Energy Transition Week.